are functions between these finite sets. Okay. But because this is our first time opening one of these scripts, I thought we'd do well to situate us within Anaconda Navigator and show how, at least on my computer, and I think this is true for many who have Anaconda installed, you might open this up. So in Anaconda Navigator, you have this whole wide array of different tools. I'm going to go into Jupyter Notebook. Note that's different than Jupyter Lab. Jupyter Notebook is the older form and is not for cloud computing more generally. It's a more lean sort of components. And I'm going to call up my my Jupyter Notebook interface. And what I need to do now is to navigate. And I apologize, but I'm going to need to navigate to the right folder. And here we go. And I will go to category theory, and I will go to events teaching and CMS. Go. And you might want to direct it on your side to your downloads folder where you downloaded that first script, 2 underbar FinSets. Okay. Now, once you point it to that, you can double click here to open it up. And you'll open up in Jupyter Notebook that file. Now, I want you to make sure that up here in the upper right, you've got a Julia kernel selected. Okay. You might have more than one. If so, pick the most recent. But that will be the Julia installation used when interpreting the contents of this notebook that we've prepared for you. So hopefully it's the right one by default. If not, you might want to select it. Xiaoyan, do you want to say anything about that further before we jump into starting to evaluate some of these components, but also first talking about this category?
No, I think I'm okay. I'm okay. Thank you.
Okay, very good. Okay, so folks, we are going to be exploring some material here whose value will extend across, sort of cross-cut for all of the material in this mini course. It will be of continued and particularly central relevance within our discussion of C-sets, of these structure preserving mappings from a schema category to FinSet or ScFinSet, which we'll use to kind of model different structures in the world, Petri nets and graphs, etc. And that's because that's mapping into FinSet. What is FinSet? FinSet is this category of sets and finite sets and functions between them. Okay, so the objects in this category are going to be finite sets, and we're going to have morphisms between them. These structure preserving mappings between them. But in a set, there's no real structure to be captured to speak of. And here, when we talk about a structure preserving mappings, it's really just a mapping between these sets. And I should have, and I'm sort of screwed up as normal, my set of slides that I had accompanied this to show little pictures of what this looked like. And I have to apologize. I'm sort of clueless in terms of showing this. Here are some supporting slides. So what is this? What do the objects in this category look like? Well, they look like, a given object here is a set. It's a bag of elements with no ordering between them, no particular structure captured relating one to the other. So it might be this two element set or this one. Show diagrams from Julia Chang's wonderful Joy of Abstraction. And we have a broader category here where each of these sets is just a dot. It's just an object. And we generally don't worry about what's inside that object. Instead, speaking categorically, our focus is on how they relate to one another. It's really that their relation that will tell us everything we need to know about it, in fact. But you should be aware, as you are learning to think about it, here you might think of each of these as a set and a finite set, and a mapping between them called a morphism or an arrow as some function mapping from one set to another. So it might look something like this, right? We might have a set 1, 2, 3, and that would be one dot here, and another set A, B, C, D, that'll be another dot. And a given function is going to specify for each and every element of the source set a particular element to which it maps over in Y. And of course, we can have more than one element in the source set that happen to map to a given element in the target set. And there may be some things in the target set that are outside the so-called image that aren't reached by that function. Here are C and D, right? So it bears noting that here there's going to be identity maps, which map like 1, 2, 3 to 1, 2, 3, where 1 goes to 1, 2 to 2, and 3 to 3. And similarly, Y too. Y also has a identity map which maps A to A, B to B, C to C, D to D. And by convention, I haven't shown those here. I could draw for each of these dots, a little dotted arrow if I wanted to, but because it's given, that's not even drawn. A key component to which we'll come back is composition, which will take two end-to-end arrows like this red one and this orange one, or this green one and then the red one, and allow us to compose them. And any two end-to-end arrows like that will be able to be composed to form a third arrow, which goes from the source of the first to the target of the second. Although by convention, we generally won't draw those. Okay, so that's sort of situating us, and I apologize for the very high-level hand-wavy treatment here, but just trying to recognize we need to balance our time. We're going to go into this Jupyter Notebook, and we're going to evaluate successive lines here. Now, for those not familiar with Jupyter Notebooks, you can press Shift-Enter, for example, to evaluate each successive line. The first, we're going to make use of the Catlab library, and we're going to define a simple function from a finite set 1, 2, 3 to a finite set 1, 2, 3, 4. Okay. And the way this is defined, again, of great importance later as well, is we specify for each successive element of the source domain what the target value is. So what we're going to specify here is that 1 is going to map into 3 for our particular function that I somewhat arbitrarily chosen. You can wonder if the next, if we had a larger set, maybe it would be 3, 1, 4, 1, 5, 9. But anyway, so 1 maps to 3 here in our function. 2, that's the one that's associated with this. This is going to encode what the mapping is for 2, is going to map to 1 here. And 3 is going to map to 4. This 4 indicates we're mapping into a set of size 4, to a fin set of 4, which you might think of, if you're thinking of this as kind of fin set, for those who know what that means, is as sort of the single category of, or single object set, which is of size 4. So I'm going to press enter, and this defines a fin function. This actually defines a function, something it knows has the properties of a function. It can be composed, it can be, we can have an identity function, etc. Now, as a function, we could map with it, right? We could map, we have some function from 1, 2, 3 to 1, 2, 3, 4. Imagine this, and our 1, 2, 3, 4. And we're going to map 2 over, right? We're going to map it over here. And what we're going to see is that 2 mapped to, well, we told it what it to map to. We told it to map it to 1, and we sure as heck better get that back, and we did. Okay, so we can, having a function, we can, something which is avowedly a reification of a function. A function is represented here. We can map it, but we can map it to a set of things at once, like to 1, 2, 3. And we can see how successively we get back these values. So we're saying, okay, evaluate it for 1, 2, 3, the whole range. And it gives us back, yes, Julia is by default 1 index. Thank you, Wade. And there's a proviso there. If you're defining arrays and you want it to be 0-based, you can say it's a 0-based array, but basically it's 1 base and 1 indexed, and it reflects, the primacy that our esteemed math colleagues place on things to begin with 1. Natural, sequences that begin with 1, rather than we in computer science have slouched to consider 0 as the base. Okay. But more than that, as a function, it has properties, right? We can ask about its domain of this function. Its domain is the set out of which it maps here, right? The object whence it comes. So that's the fin set 1 of 3. What's its codomain? What's the set whither it maps, to which it maps? Well, it's this set with 4 elements of it. Now, we can do some nicer things yet. We can take the preimage of this. So we can ask, tell me all things in X that map to, for example, 1 here. And so you may note up here, like, there was exactly 1 thing that mapped to 1. And if we ask, what value in X mapped to 1, here, the way we define things, only 2 mapped to 1. In fact, we saw that earlier. The element 2 in our fin set of 3 values, 1, 2, 3, only the second one mapped to 1. That's why this was 1, right? Okay. Now we could, moreover, so we can compute preimages, which is pretty nifty. We can also pretty print, the function definition. So we might want to say, I want to see what my function definition was, and it will tell us, okay, it was a function, each of whose, this is by implication from FinSet 3, where it maps 1 to 3, 2 to 1, and 3 to 4. And indeed, it's mapping to FinSet of 4. You notice that this could have been, 3, 1, 2, and we wouldn't have known by looking at that it's mapped to FinSet 4 compared to FinSet of 100 or FinSet of 3 or what have you. But in this case, it makes clear what the codomain is, the target of that function. That's part of its definition, that it's going from a domain to a codomain. Okay, now that's all nice. We define a function. Let's now create a new function, as it were. G1. So we have our F1. And now we're going to define G1. Okay. And this is going to map from FinSet of 4, a set with 4 elements in it, to a set with 2 elements of it. And how is it going to do that? Well, it's going to map 1 here to 1, 2 to 2, 3 to 2, and 4 to 1. Okay. So each of these guys is being mapped to 1 or 2, right? You can think of it as a binary mapping if you squint and imagine 1 is 0 and 2 is 1. Anyway, here we go. So we've defined this function G1, and we can ask, for example, is it a monic function? Meaning, in the context of set, monic will translate it to, is it injective? In other words, is this a function that for any element within our target, only at most one thing goes to it. We never have a clash between 2 things. We never have 2 things going to the same thing here. In other words, it's injective. So we might have, for example, 1 to 1, 2 to B, and 3 to D would be an injective function here. By contrast, what's shown here is not injective because we have 2 things going to the same one. In this case, it's not monic, it's not monomorphic, would be another way to say it. The term monomorphic here is going to represent a generalization of injectivity that applies across categories of all sorts. It's categorically defined. It just happens to correspond to injectivity for set. Okay, so we can ask, is it monic? I would note we could also ask, is it epic or is it split epic? I think is also supported. So here that would let us ask, is its image all of Y, for example? Here we could ask, what's the pre-image of 2? And we find, well, 2 is mapped to by 2 things in this. It's mapped to by 3. It's this one. And 4, that's that one. So we ask him for pre-image of 2 should give us 3 to 4. And indeed it does. It tells us 3 and 4 both map to 2. Right? 3, this is okay, there's a bug. Okay, this should be 2. I was futzing around with this to make something more interesting. There we go. 1, 1, 2, 2. That's what's meant. And indeed 3 and 4 map to 2. 3 and 4 map to 2. So you help me debug something. Okay. What's the domain of this function? Well, the domain is FinSet 4. We could have asked it if I did this plus, I could have said, what's the domain of G1, right? It's FinSet 4. It's going from a FinSet of size 4, a finite set of size 4, in other words, cardinality 4 to cardinality 2. Okay, and you might remember that this domain of G1 is equal to the codomain. That happens to be the codomain of our function f1 way up here. Our codomain was that FinSet 4. That was the 4 here. Right. All right. Great. Okay, well, that almost begs, it just yearns, those functions yearn to be composed, just as a vector dreams of matrices, and every fustum dreams of being a cone. These 2 end-to-end arrows, one from FinSet 3 to FinSet 4, one from FinSet 4 to FinSet 2, yearn to be composed. And compose them we shall. So here we go. We can take, to compose them, we can simply do fin function f1 and g1, but there we'll get a kind of a symbolic, sort of a higher level representation of that. It knows that the composition is something of significance. It reifies it as a thing, the composition of these two functions end to end. And that will be useful in some cases if we want to reason formally about properties. But if you just want to say, hey, give me, you know, um, a rubber meets the road sort of person, give me give me the gist of it, give me the end result. Okay, fine. You want the end result? Okay, here I'll give you the end result. There it is. So the end result is a function that goes from so what are we doing here? We're taking two end-to-end arrows from FinSet 3 to FinSet 4, FinSet 4 to FinSet 2. This one from FinSet 3 to FinSet 4 was F1. FinSet so G1 went from FinSet 4 to FinSet 2. We're composing them, and we get a composition arrow here, which goes from FinSet 3, the source of the first, to FinSet 2, the target of the second, right? There we go. And if you do the bookkeeping, it's going to go to 2, 1, 2, right? Now, this gets a little bit tedious to put this in here. And my very fiber as a computer scientist, as a software engineer, tells me there's an abstraction yearning to be born here. So I'm going to define a Julia function called force compose, whose job in life it is to take one or more functions like F1 and G1 and do force and do this force of their composition. And that's what's meant by these ... dots. We can give as many. It's kind of like var args, and you can have many of them there. And then I'll say force compose, and we get the same thing. Okay, so these functions are first-class things. Like we can do things with them. We can compose them. We can ask about their preimage. We can ask about their domain and codomain. They have this higher level of knowledge. They're not just bits of they're not just bits and bytes to be executed, right? They have knowledge of their characteristics and what they know their roots. They know whence they come and whither they go, etc. They know whether they're monic or an epic or split epic, etc. Now, but we can do more with them. For example, we can take a Julia function, a plain old Julia function, like this fearsome thing that I cobbled together. And I can build a fin function from this bit of Julia code, this bit of black box Julia code, as it were. I can declare that mapping. This is some mapping from FinSet. Well, I can make it from FinSet 4, so I can plug in any number from 1, 2, 3, 4 into X, and I could get back something in FinSet 2, because this whole thing is mod 2, and then we add it to 1. So at most we got something that's 1 here, and we can add it to 1 and get something that's at most 2, and we can get something that's no smaller than 0 here and get it to something that's 1. So it varies in the range 1 to 2. So I can define that, and then I could say map it, and I get, oh my goodness, I get these particular values. Now, you may notice, and perhaps you detect a certain malice of forethought here, that turns out to be the same function, the very same function extensionally, in terms of its extension, it's sort of observable outward behavior. It's the same function that I got from that I gave before with defining this manually. I happen to have defined this with different particular mechanics, as it were, in terms of the code than here, but it's the same old function here, right? Okay, so we can check equality between functions over as defined over sets of values. Okay, now So these are kind of nice little things, and it turns out they'll be really useful things when it comes to our instances of C sets, these schemas mapped into FinSet or Scale FinSet, because there we'll actually be characterizing things in terms of fin function. Um, uh, we'll be specifying mappings into FinSet, which map objects in the schema to particular sets in FinSet, like our favorite FinSet 4 or FinSet 3 or FinSet 2. But we'll be also, when we specify this mapping from our schema category, yeah, over to our FinSet, a morphism in our schema category will map to a function between these finite sets. And we'll be using the same syntax, the syntax with fin functions there to define what those functions are. So whether you like that syntax or not, it's going to be accompanying us through this tutorial, this mini course. And I hope you can suffer the pleasure of its further acquaintance. Okay. But we have actually extra flexibility here. It's easy to lose sight with FinSet that we actually are afforded some pretty neat functionality defining functions more generally. For example, we can define a FinSet. The syntax is a bit awkward, but we can define a finite set that has two symbols in it, y1 and y2. So before we were sort of just dealing with like 1, 2, 3, 4, as you might think about for those sort of categorical background skeleton of FinSet, where we just have one finite set of size 3 and one of size 2 and one of size 10, and we have maps between them as you'd expect, but we don't get into naming them. Here we're going to give them nice names like y1 and y2, and that will be a set of size 2, and then we're going to define a fin function that will go and map another function x, another set of different. Excuse me, I'm defining a function that will map into this fin set. And if I had my druthers, I would have gone and defined what x was. What the heck? Let's do that and complete the thought. So I'm going to say x equals FinSet. Here we go. Hey, get back there. Set, and I'm going to put x1 colon x2. The colon indicates it's a symbol. X3. And oh no, we need a square bracket. Square brackets for you. Okay, there we go. So here's our oh no, oh yes, it rearranged them. I thought I did something bad, but it arranged them per its pleasure. So it happened to arrange them x2, x3, x1. Okay, and we're going to define a function now from x, or set x, which has these elements symbolically x1, x2, x3, into our set y, y1, y2. Here we go. Ooh, look at that. Sorry. Okay. Thanks, Jushin. So what's our domain of this? Well, it's this set here. It's that set there. What's our codomain? Excuse me. No, I'm going to find another set Z, and I'm going to find a mapping from Y to Z. You know where I'm going with this, don't you? From Y to Z. And here we go from Y's. Here we go. Y's over to Z. And there we go. And now I can say, yes, they're true. The codomain of XY, as its name would suggest, is Y. And that's the same as the domain of FY, YZ. There we go. So it follows, we can compose them. They're two end-to-end arrows. There we go. and we can compose and we can get a mapping in turn from X to Z, right? We're just doing the same trick, this one, that one, and we're getting a mapping from the source of the first to the target of the second, right? Okay. Okay, I think I'm going to, just in the interest of time, we need to get on to other material. There's some pretty neat stuff that we may return to with this, like computing equalizers and co-equalizers between those functions for those who know what it is. And I leave these here as kind of teasers if anyone wants to dive a little bit deeper. But as time allows, we will come back to that in the section on equalizers and co-equalizers. So what have we seen? What have we seen here? Well, we've seen that we can characterize finite sets and functions between finite sets called fin functions. And Catlab treats these functions between these finite sets as not just bits to be executed, but as mappings, mappings with domains and codomains, mappings whose properties can be assessed, such as whether they're monic, mappings whose preimage we can take, mappings that can be composed, and whose composition is actually a sort of higher level construct, higher level bit of reified structure, but which we can evaluate, at a basic level into a simple mapping between fin sets. And we've seen that these fin sets can be defined in a way that kind of is comfortable if you know about skeleton of fin set, where we have kind of anonymous elements just called 1, 2, 3, 4, or we can compute those things with symbolic quantities involving sets of symbols, as it were, which affords us some opportunity to characterize some more meaning to the elements that might otherwise that we might want to express at something about the contents, although it's a little bit distant from the view of these as just dots. Okay, fin sets are central to our interest, and we're going to be again enjoying their company throughout much of this. I'm going to stop here at the